So today we are going to talk about logistic regression for this video. And so first of all, please try to remember linear regression. And here is our linear regression equation. And x1 to xp are explanatory variables in here, or predictors. And we have our fx, and in many cases you see them as y, okay? Y is our response variable, or nowadays you see or hear that as target variable. And what was happening in linear regression is that we are trying to explain the relationship between y and x variables by using these guys. These guys are our parameters from beta 0 to beta p. And as you may remember, beta 0 is our intercept, and beta 1s and beta 2 and to the beta p are our slopes in here, corresponding to the variable in here. And this beta 1, for example, shows the increase or decrease in the y when 1 unit increase in x1 when you think that all other variables are fixed in here. And we added a three-dimensional plot in here as an example. And this is the example from ISLR book as our reference book. And so they use this seniority and years of education of a person to find the income, okay? So now you can easily see that relationship by using this plot in here. But please keep in mind that the income in here is a continuous variable, okay? And if you try to get the idea by using this data sets, you will see that we have that income and beta 0, and we have beta time education and beta 2 seniority. And this is what was happening in linear regression. And maybe it may be a good idea to keep deeper in the topic of likelihood estimation or ordinary root square. And please go and check out for that topics if you are not remembering them, to understand how we can find that betas 1 and beta 2, okay? And if we want to move to logistic regression, it is a generalized linear model, okay? And the most important difference in logistic regression is that you have a binary categorical variable, okay? So in general, if you have a categorical variable, we are not able to use that a classical linear regression, and we are moving to another model in here. And if your response variable is binary, like a 0 and 1, and then you can use logistic regression in here, okay? And sometimes you see logistic regression as a classification methods in many machine learning books in there, okay? And we use or we assume a binomial distribution and for our outcome variable in here. And in that, we want to model the P, which is the probability of success for a given set of predictors. And we will see the details about this part in a minute. And I want to give an example for logistic regression. You want to predict whether a virus is COVID-19 or not, or whether an email is a spam or not. And these are two examples that you may have some idea about logistic regression. So to explain it in more detail, we are going to use a default data in R, and also it is explained in the ISLR book. And the response in here falls into one of two categories. It's going to be yes or no. And then, so what is that? Whether a person defaults on adapt or not, okay? So rather than modeling this response Y directly in here, in logistic regression models, we are just modeling the probability that Y belongs to a particular category in here. And these categories can be 1 and 0s in here. Generally, we think that as 1. And this is, and let's see these plots in here. You see the balance and on x-axis, and we see the probability of default in here, okay? On the left-hand side, you see that on both plots, the orange ticks indicate zeros and one values coded for default in here, okay? Some persons has ones as yes, and some people are just zeros as no in here. They are in default or not. And you see them, they are around 0 and 1. And if you try to model these data sets with this linear regression line, you see that it is not making that much sense. And even some of your probabilities are going to negative, which is not okay for us, okay? And for logistic regression, you see that instead of that line, we are trying to model the data with the S-shaped line in here, okay? And this is just the probability of default in here, and you have some S-shape in logistic regression, okay? And so for each of your X sets, you are going to find a probability of default, and then you will just find the threshold. And for this threshold and the values for response variable, the values which are greater than that threshold is going to be 1 as a prediction. And the values in Y values, which are smaller than thresholds, are going to be coded as 0 for your Y values as a prediction. Okay, please keep in mind that. And here is the estimated probability of default using linear regression. And we talk about it. And this is just the predicted probabilities of default using logistic regression. And all probabilities lie between 0 and 1. This is what we want to do in statistical modeling. Okay, we use that one. And here is another plot. Just I wanted to give you some more details about the data sets. And when we move to the application of logistic regression, we are not going to use balanced data, but it's a good idea to see some different data sets to get the idea in a much more detailed in here. And we have that balance, and you will see that the relationship in balance and income has a scatter plot in here. And we have yes or no's. Maybe you can see that the blues are no's. And then we also have yeses on oranges in here with pluses. And if you want to see that default as no, and when you check out for the balance and for the box plots, when we have a categorical variable and a continuous variable, it's a good idea to use a box plot. And we see that the yes or no makes differences in balance in here. And maybe we also have some outliers. And when you check out for income, income may not be that effective on default like in balance in here. This is how we can read about the data sets for this example. So here is the logistic model. We already seen that. This is important, guys. Just please keep in mind that instead of a line, you remember the line from the classical regression one, we are just using an S-shaped logistic function because you are just finding some probabilities. And this S-shaped just curve and just give us the probability of having 0 or 1 based on a given explanatory variable in here. This is what's happening. It is that easy. It's one of the easiest topics in statistics to understand, okay? And when you just, if you want to define it, here is our probability for given x is in here. You see that it's a conditional probability for given axis, and we just find the probability of y having 1. You can play with that part. You can say 0, but it's always a good idea to start with a y, 1. And if you try to model px using a function that gives outputs between 0 and 1 for all your values of x, many functions meet this description, okay? You will see that you have that logit function, you have sigmoid functions, and you heard lots of kernel functions even there. And they are able to give some outputs between 0 and 1 for you guys, okay? And in logistic regression, this is so using a logistic function is like a main rules in here. This is the definition of logistic function for a single predictor in here, we can just define our probability by using that logistic function, which is e to the beta 0 1 plus beta 1 x over 1 plus e to the beta 0 plus beta 1 to the x. From the definition of this guy, you can easily get the idea that your probability has to be between 0 and 1. And this guy just ensures that you have that information from your model. And after some algebra, we are using some algebra in here, and you will see that we have px, 1 minus px, and which is equals to a to the beta 0 plus beta 1x. And if you just get the log value, and you will see that it is much easier for us to use that guy. Now we are going to give a name to this definition. And so now we have the one which is we are very familiar to talk about, beta 0 plus beta 1x, okay? And when you just give it a name, this guy, px minus 1 to the px are odds. When you read about some blogs or books about this machine learning or logistic regression, you heard odds many times, okay? This is what odds. Having y as 1, the probability of having y as 1, and the probability of having y as 0, because it is 1 minus px in here. And if you just get the log value of that one, this is now a logit function for us, or log odds in here. Okay, these are the two main terms that are used in the definition of logistic regression many times. And how we are using that equation in here is that increasing x by 1 unit change the log odds by b1, or equivalently it multiplies the odds by e to the b1 in here. Okay, this is how we are talking about our regression parameters for logistic regression in here. And I'm going to give you more detail about this explanation when we are running our Xcodes for application of logistic regression. And the logit function, this guy, here is the logit function, takes a value between 0 and 1 and maps it to a value between minus infinity to plus infinity in here. Okay, this guy is from 0 to 1 in here, and now you can just map it to a value of minus infinity to plus infinity in this example. And so I want to give you some more details from a book. I just got this part and I'm going to give you the references. And the logit function takes a value between 0 and 1. I already told you guys, and maps it to a value of minus infinity plus infinity. And it's also a good idea to use that inverse logistic function. If you just get the inverse of that function, you will have this guy in here or this guy in here, okay? And also the inverse logit function takes a value between minus infinity to infinity and maps it to a value between 0 and 1. And this formulation also has some use when it comes to interpretation of the model, as logit can be interpreted as the log odds of a success, and more on this later when we will see about it. And here is the multiple logistic regression. And when you have more than one predictor in here, and generally we have p predictors, and we are easily just extend the model like that one, okay? We have log of px over 1 minus px, and now we have our general regression, and x1 to xp are our predictors, and or you can just define it at px is e to the your regression equation in here, okay? Please keep him these mathematical equations, guys. And so we have three GLM criterion in here. Maybe I already told you that our yi is coming from that binomial distribution. And we are kind of trying to just model this pi in here by using our equation, a regression equation in here. And we will just using that guy. And from which that, maybe you already seen that, we are just arriving our multivariate case of our regression, okay? And for each cases, we are just modeling our PIs in here. And so there's one example, which is coming from University of California, LA. And they just get the data, which has 4 variables, which are admit, GRE score, GPA, and the rank of their undergrad school of the students, okay? And by looking at these variables, they are trying to find if this student admitted to that school or not, okay? You will find the GRE score, GPA, and rank of their undergrad school. We will try to find if that student admitted to the grad school or not. And then you will see that your response variable is going to be 1 and 0, okay? And in this model, our aim is to build a model so that your predictor is going to be the probability of that student getting admit if you are given his profile or her profile or not in here. Okay, you have that profile and you are trying to get to predict if that student are going to be admitted to that school. And maybe by using these data sets, you can make a prediction for an unseen data. For example, you are a new undergrad school student that are about to graduate from that school, and you want to find if you are going to be admitted to that school, and you can just add your GRE score and GPA and rank of your undergrad school and try to find if your prediction is going to be 1 and 0. And if it's 0, and you can just leave it up and do not apply for that school as a general real life example in here. And now we are going to move to R to do our application in here. And this is the main reference book I use to prepare this video in here.
Wait, Professor?
To do our application in R, we are going to use the source of the data from University of California, LA. And let me just write the link in here. Here's the link, and okay. So when we have that CSV link in R, we are easily use read CSV to get the data set from the web, okay? So here is my data set. I just give it a name as DF. It is up to you guys. You can just call it anything you want. I'm going to use that read.csv function in defining R. And so we will use that link directly by using quotes inside that CSV and just get the data sets, okay? And when you see, just check out for your global environment in here, you see that we have RDF with 400 observation of 4 variables, okay? And of course, if you want to learn more about your data set, you can just use str function, and which is str in here. And when we just write that part, we see that our admit is an integer as 0s and 1. Sorry, guys. And we have GRE and GPA and rank in here, okay? And I want to get more idea about my data sets. And I generally use summary function to give summary statistics. And since all of your variables are defined as integer or numeric, and you get the main statistical definitions, statistics in here, like median, mean and max values, and first and third quarter in here, okay? Maybe you notice that there are greater number of rejects than there are acceptance. And so we get that idea because our mean of variable admits is less than 0.5. You can see it here, even just by looking at that guy in here. And since this is mean value is smaller than 0.5, which is the midpoint of 0 and 1, we can say that there are a greater number of rejects than there are acceptance for these data sets, okay? And one thing also I like to use as a starter for my data sets, to use that head function to see like the shape of my data and how it is seen in there as a tabular data set or a rectangular data set in here. When you just write head function in R, it just shows you the first 6 lines in here. And we can see that our admits as 0 and 1s in here by looking at GRE, GPA, and rank of the grad school of that or undergrad school of that student. And if you want to fit your logistic regression in R, we can just use that GLM function, which is generalized linear model. We fit a GLM in the same ones as a linear model. Please remember, we were using just LM for linear model. But in here, instead of LM, we will use GLM. And we must also specify the type of GLM in here to fit using the family arguments in here. Before that, maybe it's a good idea to convert this rank variable from integer to factor in here. Okay, it's a factor variable. And so if I want to do that, I just get my rank variable and I want to change it as factor df rank. Okay, and if you want to see how it is changed in here, maybe you will see that now we have rank and it's just defined as a factor from 1 to 4. And you see that for each of these rank, you have that much number of students in there. These are just giving the frequencies in here. And just write str, and you see that this is a factor with 4 levels. Okay. And I want to generate a linear logistic model by using GLM in here. I have admit versus GRE plus GPA plus rank. And then the family is going to be binomial. Okay. And maybe it's a good idea to give a name to your model in here. I write it as logit, okay? And I run in that one. And maybe admit is not there. Let's see, I have admit not found. Maybe I should give the data here, of course. So you should also define your data sets inside your function, okay? And I'm just defining that one in here. And now you see that this is very, very familiar to the linear model that we were using just LM. And now in here, we just write family as binomial and also define the data sets in this code. And now we will use summary function to see the data details about the output of these data sets. So let me use summary for my model, and then I can just get the summary of my logic model that I defined in here. Now, as a first step, you see that call, which is giving your model in here, and we see our residuals or the deviance of our residuals, and you see that it's around 0, and it's a good sign for our model in here. And when you just check out for your coefficients, first of all, we have our estimations. And now we can do some interpretation by looking at these guys in here. You see that we had GRE and GPA estimations and the p-values, which are kind of important for us guys. And now, since rank is a factor variable, we have the estimations for each levels of the factors except the reference one. So when you just check out for GRE, let's say, as the first one, okay, let's see, we have our estimation in here as 0.002. And we can say that each 1 unit change in GRE will increase the log odds of getting admit by 0.002. And it is p-value indicates that that is somewhat significant in determining in the admission. So you can say that your GRE score is important to get admitted to that university, okay? And we can do the same or similar interpretations for GPA. But when you move to the rank in here, the interpretation of rank is different from others. You can say that going to rank 2 college from rank 1 college, when you just check out for this one, okay? Going to from rank 2 college from rank 1 college, which is reference 1, will decrease the log odds of getting admit by minus or 0.67 in here. And going from rank 2 to rank 3 will decrease it by minus 1.34 in that, okay? And when you just check out for the null deviance in here, which is the value when you only have the intercept, okay? Null deviance is that you just have your model by adding only intercept and run your model without your predictors in your equation. And the residual deviance is the second one. The residual deviance is the value when you are taking all the variables into account in here. And you want to see how this guy is changing when you add your variables. And it's a good sign that your deviance is just reduced in here, okay? And greater the difference, better the model, okay, in here. Greater the difference between null and residual deviance is a sign for a better model. And it makes sense to consider the model good if that difference is big enough in here. And when you just remember our logit model and logit functions in there, and maybe if you want to get the exponentiated coefficients, and you can just use the exp function in there. And the object you want to exponentiate is called coefficients, and it's a part of logit in here. And so how we are running that part is that after talking about the output of our model, we can just use exp coefficients of our logit model. And we have intercept, GRE, GPA, rank 2, rank 3, and rank 4 coefficients in here. These are kind of different than these guys. And you can say that for a 1 unit increase in GPA, let's see, we are talking about these coefficients. 1 unit increase in GPA, the odds of being admitted to grad school versus not being admitted increase by a factor of 2.33, okay, in this example. And we can make the same interpretations for rest of our coefficients in here. Predictions. Now I will talk about the predictions in our logistic model. Let's see. So we are just starting by calculating the predicted probability of admission at each value of rank, and we will hold GRE, GPA at their means in here, okay? First of all, we want to create a new data set to find some predictions in here for, like, you can think that one as a test data set. We have train and test data set. And now we have new data. I call it as new data 1 or just new data. Let me just call it. And so I will just generate it by using with function. I have my df, which is my main data set I'm using so far. I want to add a data frame in here. And let's see, my GRE is going to be mean. I'm generating a new data set by using my variables in there. It's going to be a data frame from df. Now I'm going to get the mean of GRE, okay? And also as GPA, I want to change it as mean value of GPA, okay? And the rank is going to be same as factor, which is like the original data set, from 1 to 4. And here is my new data sets in here. If you want to see it, you can just click. And now, instead of all values, now we are trying to calculate the predicted probability of admission at each value of rank in here. Let's see, you have a mean of GRE and mean of GPA. And now we want to see how it is changing by rank, how it is changing by rank in here, okay? So let's move here. I want to add a new column to my data sets as rank P. Let's see, this is my prediction. I want to predict the rank or the admission by looking of each levels of rank. And you can easily use that predict functions defined in R. So use my Logistic Model, and I want to just use the new data, and which is new data 1. And the type in here is going to be response. Okay. Now, to get the predictions for admission for these new data sets, I'm just using predict function. And here is the name of my logit. I already defined that logit in here. Okay. And my new data is new data 1 that I just defined it before. And the type is going to be response. I'm just looking for the response predictions in here. When you run that part and just run your data one more time, now we have another column, which is our new column in here. And we can see the probability of admission if you have the mean value of GRE and GPA for you guys. And the undergrad school of yours is the rank 1, then the probability of having that admission from that school is 0.51, okay? And the predicted probability of being accepted into a graduate program is almost 52 for students from the highest prestige undergraduate institutions in here, okay? And the same probability is 0.18 for students from the lowest ranked institutions holding GRE and GPA at their means in here, okay? And if you add a threshold in here as 0.5, then you will get 1 for this one and zeros for these guys in here, okay? And these are the predictions and that we can do by looking at our model in here. And also these are the references. Let's see. These are the references in here I use to prepare this application in here.